Famous NBA players such as Stephen Curry and Ray Allen were praised for their ability to make consistent basketball shots. However, without the help of physics and complex biomechanics, these famous players would not be where they are today. When comparing these elite-level players to our high school basketball team, we knew that there is a huge skill gap between them in terms of shooting the ball consistently and efficiently. While we knew this was most likely due to the fact that most of the players were beginners, we wanted to take a deeper dive into the underlying factors. We also wanted to conduct a study that would be beneficial to the shooting performance of our team, especially since two of us are a part of it. Prior to our study, we conducted background research on the different aspects that go into proper shooting forms. In this research, we found that the most recurring factors were the effect of the angle in joints such as the elbow and knee when bent. By synthesizing our findings, we formulated the question, what is the effect of coordination between the range of motion of upper and lower joints on the shooting of high school basketball players? We then hypothesized that an increase in the range of motion in both the lower and upper body joints would allow for a higher ball velocity in the jump shots of high school basketball players. Lastly, when we mention range of motion, we pertain to the extent to which a joint is bent from its starting position.
In order to collect the data to either refute or accept our hypothesis, we worked in coordination with USC officials and graduates, as well as the biotechnology group Biotech. We were able to measure the overall degrees of motion of a shot before it leaves the player's hands. Equilibrium sensors were attached at the specific points of the body on the forehead, chest, thighs, trunk, knees, feet, biceps, and wrists. Participants of the basketball team were assigned to 3 different basketball courts and conducted at least 10 free throws, making a minimum of 3. For reference points, the bentmost position of which all parts of the body were locked prior to shooting where the measurement initially began. This would then end at the extended position where the player would elongate their body in order to push the ball from their hands, allowing us to measure the full body degrees of motion. Additionally, a high frame motion capture camera set up perpendicular to the shooter in order to see the overall arc of the basketball when it is released from the body was used until it hit the ground. The website vernier would then be used in order to measure velocity and the peak height of which the ball was in its arc. Using the equilibrium sensors, we were able to measure the joint angular degrees of motion from the lower most bent position to the extended position of the shot. Results displayed that both made and missed shots took around the same amount of time, from 0.3 to 0.4 seconds, from the starting to end shot position. Additionally, as each of the 3 participants were right-handed dominant in shooting, there was a common trend of increased bend in the comparison to the non-dominant hand. However, similar ranges of motions are displayed by the dominant and non-dominant sides of the legs. Using the made shot analysis results of AJ, Gabriel, and Jonathan, we created graphs to display any common patterns. This graph displays the shoulder range of motion compared with the knee and ankle ranges of motion. The independent variable represents the upper body while the y-axis represents the lower body. As shoulder angular motion increase, knee and ankle motion decrease, just displaying a negative relationship. However, different results were evident when the upper body is switched with the elbow degrees of motion. In contrast, as elbow angular motion increased, the knee and ankle motion increased, creating a positive relationship. What can be interpreted from this data is that different parts of the body in made shots specifically showed that the lack or increase of degrees of motion in one area of the body can be accommodated by using an opposing part of the body.
Using Vernier video analysis software, a made and missed shot of the 3 participants were studied to understand the difference in behavior among each shooter. The 2 aspects that were most taken into consideration were the immediate velocity of the ball upon release, as well as the maximum height the ball reaches before falling. We plotted the aerial pathway of the basketball by 5 frames, starting from when it was released to when it reached the basket. The software provided both the vertical and horizontal vectors when the ball was launched, therefore the approximate rate of change in both directions were recorded. Using the Pythagorean theorem to find the hypotenuse of both vectors, we could now record the ball's immediate velocity. In addition to this, we scaled the distance from the free throw line to the baseline at 19 feet and converted to meters, so the maximum height the ball reaches could also be recorded. In our findings, of the 3 that were analyzed, Gabriel's result was most statistically significant. He had the highest immediate velocity at 7.3 meters per second and the highest arc of 6.687 meters. What most likely contributed to this was Gabriel had the highest elbow flexion out of the 3 participants. By analyzing the data collected through the Biotech sensors and Vernier video analysis, we found that there is significant coordination of angular movements between the upper and lower joints. As the shoulder moves at a larger range of motion, the knees and ankles position at a higher depth, and the elbow flexion makes the same joints bend lower. Elbow flexion during a jump shot has the most apparent effect on both the velocity of the ball when launched and the final arc of the basketball. Therefore, in order to improve the efficiency of the motion, you must take all elements into consideration.